Hi, everyone. It's my great pleasure to introduce our speaker in this special format. And Xuezhe also go with Max. Ma is a PhD candidate and CMU advised by Ed Hovy. He has a lot of work. He sits in the intersection of NLP and machine learning, and he has a lot of work of deep learning and representation, learning with application to information extraction, structure prediction, and generative models. And he had won the AI2 Outstanding Intern Award and several paper awards at ACL conferences. So it's my great pleasure to have Max here to introduce some of the work he has been doing for his PhD. And let's welcome our speaker. Okay.
Okay. Thanks, Nayin, for the introduction. And I'm very glad to give this talk. Today, I'm going to talk about my research towards structure-infused and disentangled representation learning. Okay, let's start. In the past years, we have witnessed the successes of deep learning in various applications, including automatic driving, speech processing, question answering, and machine translation. So the question is, what makes deep learning work? And I think the first reason is we have big data. For example, a large volume of images or texts. And the second reason I think is that deep learning changed the way we extract features from data. So traditionally, we rely on manually designed features with our expert domain knowledge. For example, the scale invariant feature transformation for images and bag of n-grams for text. But obviously, this is costly and not scalable. Deep learning, on the other hand, learn these feature representations directly from data with neural networks. And with many well-developed neural architectures, we can simply import one of our favorites. Then on top of these neural networks, we applied machine learning algorithms to complete some tasks, such as classification. And learning a neural network involves learning a neural network involves a forward pass and a backward pass. In this forward pass, we calculate a loss function, and during the backward pass, we propagate the gradients to optimize the whole system. So then we can automatically learn feature representations directly from data for the end task. And this is why deep learning is also known as representation learning. And in recent years, researchers keep pushing the performance of deep learning models to be better and better in various tasks, for example, the image classification. And this talk focuses on two problems in deep learning or representation learning. The first problem is how to apply representation learning method to predict structured outputs. And the second is how can we better understand the learned representations by decoupling the underlying factors. So in the first session, I will show you how to handle structure predictions by representation learning. So before diving into the methodology, I want to first describe the difference between structured and unstructured prediction tasks. In structured prediction, the output Y consists of a single component. For example, in classification, Y is just the class label. On the other hand, in structured prediction tasks, Y consists of multiple components. For example, in syntax parsing, Y is the parsing tree of the input sentence. And a single component of Y is a dependency arc in this tree. Machine translation is also a structure prediction task, where Y is a sequence of words in the target language. The second property of structure prediction is that the output components are highly correlated For example, in machine translation, the output should be a valid sentence other than randomly independent words. And the third property is the output space is exponential. So we need to design efficient decoding algorithms instead of enumerating all the candidates to search for the optimal output. So back to the deep learning framework. So to apply deep learning models for structure prediction tasks, we need to design structure algorithms. And importantly, we need to ensure that every step in the structure algorithm must be differentiable so that the gradient can be propagated to learn the neural network. And the second problem is the efficiency of the decoding algorithm. And in practice, most decoding algorithms are inefficient because they are not parallelizable. So as a researcher in natural language processing and machine learning, one area of my research is to develop deep neural models for structure prediction tasks, such as sequence labeling and dependency parsing. But in this talk, I'm not going to talk about these models. And the reason is that even though this model achieves outstanding performance, but they still suffers these problems. And in this talk, I want to further ask, can we get rid of the structure algorithms for structure prediction by using representation learning techniques? So in the first part of this talk, I will introduce our recent work on non-autoregressive sequence generation to show how to encode structure independence into representations. Okay, first let's see a structure prediction task, sequence-to-sequence generation, with seq-to-seq generation in short. In seq-to-seq generation, both the input X and the output Y are sequences of tokens, and we want to model the conditional distribution of Y given X. And it is straightforward to formulate machine translation as a task of seq-to-seq generation. Due to the structured output Y, it is difficult to directly build a model for the joint distribution. And a common strategy is to use the autoregressive factorization. That is, the probability of the next token is conditioned on the tokens in front of it, which is called the history. And here is the diagram of the graphic model for autoregressive factorization. We see that for every token, it depends on all the previous tokens. Based on the autoregressive factorization, the most popular neural architecture for seq-to-seq generation is the Encoder-Decoder Architecture. And here I will use the machine translation example to briefly introduce it. So first, we have an encoder network. It encodes the source sentence into its hidden states, which is one vector for each word. And then we go to the decoder. It first computes the hidden state of Y0, which is a special token to indicate the start of the target sentence. And then with these hidden states, we compute another vector, which is called the context vector or semantic vector. And using it, we can compute the first term in the autoregressive factorization. And then we go to the second step for the second term, and then we continue until we complete the whole sentence. And the decoding algorithm follows a sequential procedure. So first, we compute the hidden state of X, and we start to translate the first word by selecting the best word for this step, which is max. And then this word will be fed into the decoder for the translation of the second step. And this continues until we translate the target sentence. So actually, it's a greedy algorithm. So in practice, there are some problems for this model. The first is the sequential decoding algorithm, which is inefficient because it is not parallelizable. And the second is the error propagation. That is, errors happened in previous steps will be propagated to the later ones. And beam search is commonly used to mitigate error propagation, but it makes the decoding even slower. And due to these problems, we need to ask if we can turn to non-autoregressive models for seq-to-seq generation. And a naive solution is to assume that given the input sequence X, the output tokens are independent. But obviously, this assumption is too strong to be feasible in practice. To improve the naive solution, we propose to introduce a set of latent variables Z. And the non-autoregressive assumption can be achieved by assuming that the output tokens are independent given both X and Z. Okay. Then we need to ask, what are the advantages of this formulation? So the first one is that the independent assumption is indirectly between X and Y. It is through the latent variable Z. And the second is the efficient decoding via a two-step procedure. So we first find the optimal Z, and we can parallelly decode each token based on the non-autoregressive assumption. However, this model raises new problems. First is how to compute the integral in the likelihood function. And the second is, in order to satisfy the non-autoregressive assumption, they needs to be sufficiently expressive to encode all the structured dependencies of Y and how to handle it. So in the following session, I will introduce how we address these problems. And the first is the computation of the integral. And here we use variational inference. So in the framework of variational inference, we replace the integral in the likelihood function with its evidence lower bound. So in this framework, we have three distributions to model: the posterior, the prior, and the generator. And here, I will use a diagram to briefly present the whole process of variational inference. So first, we have our data. Here, we omit X in this diagram because X is the conditional input to every term in elbow. And we first input Y, our data, to the posterior distribution to compute the latent variable Z. And at the same time, we assume that Z follows a prior distribution. And then we input Z to the generator to reconstruct our data. And this is the framework of variational inference to approximate the likelihood function. Okay, now we know how to approximate the integral with variational inference. Let's turn to the second problem. That is how to design the latent variable Z. So here we design Z to be high dimensional because we believe that a low dimensional vector does not have the capacity to encode all the structure dependencies of Y. And concretely, we design Z to be a sequence of vectors with the same length of the output sequence. And with the posterior distribution, we map X and Y to Z by assuming that at each step, Z follows a normal distribution. So here, the mean and variance at each step are modeled by neural networks. And with the same machine translation example, we briefly introduce the design of Z. So first, we compute the hidden states of X and Y, and then the context vector for each step. And with these context vectors, we compute the means and the variance for the posterior distribution. And with this design of Z, we expect that Z is sufficiently expressive to encode all the structured dependencies of Y. Okay, now with high-dimensional Z, the next question is how to model the prior distribution. And here, we use generative flow, which is an elegant technique to model complex distribution. So basically, a generative flow defines an invertible mapping from a complex distribution to a simple one. So for example, the distribution of X here is complex, and it is difficult to directly build a model for it. But if we can find an invertible transformation F to map X to a normal distribution, then we can compute the distribution of X by the change of variable formula. So formally, the distribution of X is defined by the distribution of gamma, which is just a normal distribution, and the determinant of the Jacobian matrix. So in practice, we need to design the transformation F to be so that the Jacobian matrix is efficient to compute. And also, a single transformation is probably too weak, and we can stack a series of such transformations to form a generative flow. Okay, in our model, with X as the conditional input, we use generative flow to transform Z to gamma, where the vector of gamma at each step follows a normal distribution. The generative flow also provides us with an efficient decoding method. So remember that in our decoding method, we need to first find the best Z according to our prior distribution. And this can be approximated by just taking gamma as 0, because 0 is the unique mode in the normal distribution. Okay, to illustrate the decoding process in our model, so the first step is the same as before. We compute the hidden state of the input sentence. And then the generative flow takes the hidden states together with gamma as input to compute Z, the latent variable Z. And when these states are ready, we start to translate the target sentence. So since our decoder is non-autoregressive, we can simultaneously compute the context vectors and parallelly decode the best word at each step. And we see that all the decoding steps can be parallel. Okay, to evaluate our model, we evaluate it on machine translation with 2 pairs of languages, German to English and Romanian to English. The performance is measured by blue score. Basically, higher blue score indicates better translation quality. And the baseline model we compare with is the NAT model, which is similar to the naive solution mentioned in previous talk. And we see that our FlowSeq model achieves significant improvements over the baseline on both these 2 language pairs. However, FlowSeq still falls behind with autoregressive models, and we leave further improving the FlowSeq to future work.
Can I ask a question? Categories.
Okay. Sorry. Sorry.
Hi. Can you hear me?
Yeah, I can hear you. Yeah.
So, how do you determine the length of Z and thus Y in inference?
Sorry. 2 people are speaking at the same time.
I'm sorry. I'm in a noisy room. How do you determine the length of Z and thus Y at inference time?
Okay. So in the inference time, we train a classifier to predict T together with the model, with using the X as input.
You predict the length of Z as well?
Yes, we predict the length of Z. We train a classifier to predict the length of Z at the same time when we train the FlowSeq model.
Is that just like a literal, you're predicting the number 1 through some max, or are you predicting like an off by 1, like a +1, -1 kind of length? Or?
Yes, we predict the difference between the source and target languages, sentences, sorry.
Okay, thanks.
Okay, let's continue. Since efficient decoding is an important motivation of this work, so we compare the translation speed with autoregressive models. So first, we compare the translation speed with respect to the length of the target sentence. And here, the y-axis is the average decoding time for one sentence. And we can see that as the sentence length increases, the FlowSeq model achieves almost constant decoding time, while the decoding time of autoregressive model is increasing linearly. And second, we also investigate the translation speed in the sense of batch size. So here, to make the comparison clear, we add a red line to show the relative decoding speed up. So unsurprisingly, for both the two models, decoding is faster when we use larger batch size. But FlowSeq is more friendly to batching because you can see the speed up becomes larger as when we increase the batch size. Okay, now I think I can summarize this work. So we propose the FlowSeq model to encode structured dependencies in latent representations. And to achieve this goal, latent variables are designed to be high-dimensional, and the distribution is modeled by generative flows. And with this model, we achieved a non-autoregressive sequence-to-sequence generation model to avoid the sequential decoding. And this is a general framework which can be applied to other structure prediction tasks, such as sequence labeling or syntactic parsing. Okay, I want to ask, before I move into the next session, are there any questions? Okay, cool, good. Now let's move into the second part. So in this part, I'm going to talk about how to decouple underlying factors to better understand the learned representations. So now we know that deep neural networks are good at automatically learn abstract feature representations for the end task. However, it raises new problems. First, it requires a large amount of labeled training data, and we need to ask if we can learn meaningful representations in unsupervised setting. And second, the learned representations are too abstract to be understood by human. So someone may ask, is abstract feature representation a real problem for us? So let's see to answer this question, let's see the machine translation example. So we know that a core ingredient of translation process is to capture the meaning of the source sentence and rendering them into a target language. And during this process, the translator needs to capture linguistic information from different levels, including the morphology, the syntax or grammar, lexiosemantics, sentence semantics, and sometimes even pragmatics. Now, a deep learning system tells us that all this information has been captured in one representation. So should we trust this system or not? So personally speaking, I won't trust this system. But if we can tease apart these different sources of information into different representations. This system will be more explainable and trustable. So this is called disentanglement. And in this following session, I will introduce our recent work focuses on these two problems. That is, learning decoupled representations from and for data generation. So to learn meaningful representations in unsupervised setting, we select generation as our objective. So basically, generation is to learn to generate new data from samples. So for example, given a bunch of images of cats, and we want to generate new images. So why do we choose generation as our objective? Obviously, the first reason is that it requires no label data. The supervision is just the data itself. And the second reason is that in the generation process, all the underlying factors of data must be preserved. And this is important for unsupervised representation learning and for disentanglement. So in addition to structure prediction, I have also worked on developing deep generative models and applying them to representation learning. And in this talk, I'm going to talk about one work in this line of research, that is decoupling the global and local representations for image generation. So in this work, we need to address two challenges. The first is the entirely unsupervised setting. So since we use generation as the objective, there is no explicit supervision to navigate the model to learn the desired desired representations. And the second is how to decouple the local and global information of an image into different representations. And the key idea of this work is to utilize the inductive bias from the architecture design. So I will use a diagram to illustrate the high-level insight of this work. So here we denote the input image as X. And first, we feed X into an encoder to compute a latent vector Z. And importantly here, the encoder is designed to be a compression network, which compresses the high-dimensional image X into a low-dimensional vector Z. So the local information of X is enforced to be discarded during this compression process. And Z is supposed to capture more global information of the image X. And then we feed Z as a conditional input to an invertible decoder, which transforms X into a gamma. Here, gamma has the same set of X. And since the decoder is invertible, with Z and gamma, we can exactly reconstruct the image of X. And this reconstruction process can be regarded as an addition operation. That is, we add Z and gamma to compute X. So in this way, we expect that the local information discarded in the compression process would be restored in the local representation gamma. And this is how we decouple the global and local information. And the key point is the architecture design of the compression encoder and the invertible decoder. Okay, so in practice, we use variational inference to learn the global Z and the generative flow to model the invertible decoder. To evaluate our model, we conducted two groups of experiments. The first group is to demonstrate the effect of the decoupled representations, and the second is for the image generation. So the first experiment is called switch operation. So it is to switch the global representations of two images to decode new ones. So suppose we have two images of frogs from the Cypher-10 dataset, and first we encode them respectively to their global and local representations, and then we switch their global representations to decode new images. And we can see that this model switches the skin color of the two images of the two frogs. And here is another example of horses from Cypher-10. And we see that this model switches not only the colors of these two horses, but also the backgrounds of these two images. And these are two images from the bedroom dataset. And the model can switch the style of the two bedrooms to get new images of bedrooms in different styles. And for human faces, we see that the model switches the colors of the skin and hair. Okay. In addition to the switch operation, we also perform image classification. And the idea is to train a linear classifier on top of Z and gamma to measure the class information captured by these representations. And here, image X is the baseline. That is, we directly train a classifier with the pixel as the features. And we see that with global Z as features, the classification accuracy is much better. And moreover, the accuracy of local gamma is even worse than the baseline. So it indicates that Z captures more global information describing the entire image, while gamma captures more local dependencies. And we also compare our model with DeepInformX model, which is one of the best compressed representation learning methods using mutual information as the objective. So we see that the accuracy of global Z is better than DeepInformX. And for image generation, we want to evaluate how realistic the generated images are compared with real ones. And quantitatively, we measure the FID score, and qualitatively, we show some random samples from our model. So for FID score, it defines the distance between the real and generated images. So lower FID score indicates more realistic generation. And the baseline here we compare with is the GLOW model, which is the generative flow model we use as the encoder. So to compare with GLOW, we can evaluate the effect of decouple representations on image generation. So we see on 3 datasets, our model achieves lower FID scores over the baseline. So it demonstrates that decoupling these global and local informations is also helpful for image generation. And here are some random samples of the human faces. And we see that these images are realistic, but there are still some issues for this generation. So for example, the modeling of the hairs is still challenging. Okay, I think I can summarize this work. I think the takeaway message of this work is that with only the architectural inductive pairs, it is possible to learn decoupled representations via generation without using any explicit supervision. So from the perspective of inductive pairs, I want to further discuss representation learning and the future work. So when we talk about representation learning, we need to ask a general question. So where the inductive biases come from to navigate the model to learn the desired representations. And one attractive direction is to use the domain knowledge, just as we use them to design features. So for this direction, we have worked on formulating domain knowledge as logic rules, using structured laws, adding sparsity constraints, and designing controllable regularizations. And we can summarize this direction as neurosymbolic AI. However, sometimes domain knowledge is also expensive, and it is uneasy to formulate domain knowledge into the end-to-end learning paradigm, because we need to ensure that all the operations must be differentiable. And I think an alternative direction is to utilize the inductive bias from the neural architecture. And the two works presented in this talk is a small step towards this direction. So in the future work, I want to explore architectural inductive bias for representation learning from three aspects. So the first is to further my research on unsupervised and weekly-supervised representation learning. And the second is to use disentanglement to learn interpretable and controllable representations. And at last, I want to explore the potential to establish a framework to link the architectural variance with learned representations, which services as a long-term goal. So for unsupervised and weakly-supervised representation learning, one ongoing project is to learn interlingual representations from and for multilingual machine translation. And the idea is that with parallel corpus between different language pairs, we try to learn an interlingual representation which is language independent. And through this representation, we can perform translation between every pair of languages. And another project is on medical image processing. And we want to automatically detect and localize the disease by medical image generation. And here is an example of the brain lesion localization. And we want to build generative model for these brain images to learn to represent the location of this disease. So for interpretable and controllable representation learning, so I want to first stress why should we care about interpretability and controllability. This is a headline from Harvard Business Report, which says that even some AI systems report performance better than doctors, patients still don't trust them. And what is worse, self-driving techniques can cause severe accident when the car is out of control. And in 2017, the European Union published a regulation saying that every algorithm must be accompanied with an explanation. So all these examples lead to a central question: how to explain and control deep learning models. And I think disentangled representation learning is the potential direction. So by disentangling the causal factors, we can tease apart the dependencies of data and connect the output representations with the input factors. Then deep learning models built upon disentanglement will be more accountable for their predictions and will be able to perform error diagnosis. Moreover, through disentanglement, we can better control the dynamics inside the model, and we can and make the outcomes more predictable. So at last, with the long-term goal, I want to explore how to connect the architectures with representations. We know that deep learning researchers have developed many successful neural architectures. However, the impact of these architectures on the output representations are still unclear. So the inductive bias from these architectures are only based on our intuition or some empirical evidence. So if we can establish a framework to analyze this impact, we can better understand these architectures, and this it can serve as a guidance of developing new architectures. But obviously, this is challenging and it's a long-term goal. Okay, these are my collaborators, and I really appreciate their efforts and help. And this is my today's talk, and I would like to take questions.
Okay, any question from the audience? I can already see there in the chat. Avijit asked the question. Do you want to just ask it while this?
Sure. Okay, the question is, what forces the compression network of Z to capture global features and the added gamma to capture local features? Why isn't it the other way around? For example, the Z captures global and gamma captures Z captures local and gamma captures global. Okay, I think this is I think the reason why the Z can capture global information and gamma captures local information is that first is the architecture of the encoder network. So for the encoder network, we design it to be a compression network. So the output is a low-dimensional vector, and in this architecture, we also use some normalization layers to enforce the network to discard some spatial dependencies of the image. And for the decoder, for the gamma distribution, for the gamma representation, because the generative flow model is invertible. So with Z and gamma, we can exactly reconstruct our image X. And so since Z is enforced to capture global information, then gamma should capture more local dependencies. And another reason is that there is some evidence, empirical evidence, showing that the generative flow model is better at capturing local dependencies than capture global information. But this is only some empirical properties of generative flow model. So we utilize both these two properties to achieve the decoupling of the global and local information.
Yeah, thank you.
Okay, here is another question.
Greg, maybe you can directly ask the question. We still have time. We have plenty of time. Yeah.
Oh, great. Yeah. Hi, this is Greg. Can you hear me okay?
Yeah. Yes, I can hear you.
Great. Thanks for the talk. That was really interesting. I was going to ask if you could talk about, so I can kind of remember a few different ideas about combining VAEs and normalizing flows, like you did. I was wondering if you could comment on like some of the differences. So as I understood it, you were using the flow to model like the residual, like the error, and my memory of some of these other ideas is more like they learn a VAE and then use a flow model on the latent space to transform it from a Gaussian to some other distribution. Am I understanding this kind of relationship right, or can you comment on that?
Oh, okay, sure. So basically, in the framework of variational inference, there are three distributions, as I mentioned. So it's the posterior distribution, the prior distribution, and the decoder or the generator, right? And so for all these three distributions, we can either use some assumptions like we assume them to be Gaussian, or we can use generative flows to make it more complex. It depends on the motivation of the model. So if we use generative flow to model the latent space, for example, we use generative flow to model the prior of the posterior distribution, and then the motivation is that we want to improve the expressiveness of the latent space, or we assume that the Gaussian distribution is not expressive, is not sufficiently expressive. So we want to use more complex prior or posterior distributions. I think the first work I present in this talk is in this line of research. That is, we use generative flow to model the prior distribution to make it more complex, so that the latent space can capture more information of the data. And the second work, we use generative flow to model the generator or the decoder. So the motivation is that we want to utilize the property of the invertible property of the generative flow. Because if we use generative flow to model the decoder, then we can exactly reconstruct our image to achieve the generation. So that's the two different motivations of how to combine generative flow and VAE.
Thanks, that makes sense. Yeah.
Can I ask about if you can you go back to the slides where you show the qualitative transfer using global and local?
Qualitative, right?
Yeah.
Here, right?
Yeah. So I'm trying to understand what you consider to be global and local in terms of properties here. It was really unclear to me. Like, I mean, they're horses, right? But like, there's the local things that make this one particular horse look like it does, and then there's things like the color or the background or the style, and it's really unclear to me what specifically universal properties are disentangled one way versus another.
Okay. So I think yes. So that's the I think that's the one like challenge of this work. So because we do not have the explicit separation, so all these inductive pairs are from the architecture. So when we see these demos, we can see that in our model, the global information captured by Z is more like the style or the color or some like I don't know, the illuminating conditions of the image, while the local information is more like the shape or the edges of the object. So so we can see that
if that were the case, then I wouldn't expect the classifier result to be as good as it is, because right, like overall color and shape is not going to be predictive of class, whereas the contours might actually be. So like, are these completely separately trained instances that just happen to have the same architecture? Or can you actually train a model that is good at classification and also gets you the qualitative transfer, like the same literally trained model will also do a good job of transferring between the brown horse and the...
So first, I think the answer to the first question is like the classifier is separately trained. So we so when we finish the training of the generative model, we fix the Z and gamma and train a classifier on top of it. So yes, I understand your question. So that is
but it's the same Z and gamma. It's the same. I understand you train a classifier on top of that, but the Z and gamma that you've trained, you're using the exact same parameters to get that representation for the thing that goes into the classifier as what you would use to do the horse coloring, like, or versus doing a whole new Z and gamma training.
Yes, this is the same like representations I use for the transformation and for the
same parameters
yes.
too.
Yes, the same parameters. Yes. And I think the question is if the global Z is capturing more information about the style or the color, so why it can achieve the better classification accuracy. So I think one reason is like maybe this this kind of like style information or color information is also useful for the prediction of the image class, because in Cipher 10 there are 10 classes, and there are 10 classes of images, and maybe there are some superficial features that we can utilize to make the prediction, and C captures this kind of features. And yes, I think the reason, because we see that the classification accuracy is still not very good. It's only like below 60. So I think that's the reason, that the local gamma z is, because the local gamma z is not there. So only with the local gamma is not there. So only with the global information, the classification accuracy cannot be very good, because the local dependencies, like the shape or the edges, the information has been discarded. So that's the reason. Yeah.
Very interesting. Thank you.
Mm-hmm.
Are there any other questions from the audience? Okay, I actually have several questions for your first work. It seems to me it's like you're doing a VAE. It's just not auto encoder, in the sense that you're predicting Y, not X, right? So the whole thing can be basically applied to any generation task.
Yes.
Which is
yes.
not translation, but more of a language modeling and generate in a monolingual setting. I wonder whether you have any insight on that. Do you think if you just training to do the generation, whether it will work reasonably well, or whether there will be challenges?
Yeah, I think it will. If we apply this FlowSeq model to general generation task, not the 6-to-6 generation task, then it will be more challenging, because in 6-to-6 generation we have the input sequence, which can be used as a conditional input, right? So condition on this input X, the distribution of the output sequence Y is somehow not that flexible. But if we want to apply this model to general language models, then the distribution of a sentence X is more flexible. And based on my observation, the expressiveness of the generative flow models now are not sufficient to support that kind of complex distribution. Yeah, so we need to design more powerful generative flow models to make it feasible.
I see. But do you think that will be useful for like style transfer, that type of generation?
Yes. For style transfer, I think for style transfer,
you need some disentanglement, probably. You need some disentanglement, maybe like combine the second work and the first work in a way.
Yes.
I don't know.
Yes, and I think the one challenge is that generative flow can be only applied to continuous random variables. And if we want to apply it to languages, then we need to think about how to transform languages to continuous space. And because in my first work, we only use generative flow to model the latent space, which is continuous, then it is fine. But if we want to apply generative flows as decoder in language space, then it is still challenging.
Oh yeah, I was more of you have that Z, and then you disentangle them, and then you apply some flow, and then you combine. Or
yes,
yeah.
Yes,
anyway,
yes.
I just felt it's very interesting. Oh, and another is more of a high-level, very philosophical question for your second work, this disentanglement. Do you think it's possible to do some of these more of like your model can decide how many factors are there, and you can automatically disentangle into that many factor, the K factors.
The K factors. What do you mean by factor? Oh, you mean here? Actually, here we only consider like two factors. One is we define as global, and one is defined as local.
Yeah, definitely. And I see a lot of this disentanglement work was like two, or usually two. And I wonder whether people have been thinking about, because there will be many latent factors, and I see some. Okay, there were some work on they can use like eigenvectors, eigenvalues to decide like the largest eigenvalue was the first factor. So I wonder whether you have been thinking about this problem and whether this is easily extendable to those type of
yes, I think that's a very I think it's a very interesting direction. And actually we are trying to perform some experiment to see if we can explain the an individual factor of in Z or in gamma. I think that is challenging because the dimension of Z and gamma are still very large, and if we only control one of the dimension of Z and gamma, it's not clear what it related to. But a good part is that in our model, we assume that Z and gamma follows the normal distribution, so it is intrinsically independent. Distributionally independent. So we are still performing some experiments to see if we can explain some individual unit of Z and gamma. Yeah.
Okay, great, thanks. There is one more question in the chat.
The question is, can you please just restate how to find? How to find the global and local Z and gamma works. Okay, let's turn to the diagram here. So here, we first input X to an encoder network and to compute the latent variable Z. And here, the encoder network is designed to be a compression network. That is, it inputs the high-dimensional image X and output a low-dimensional vector Z. And in this network, we use some normalization layers to force the network to discard some local dependencies. And then, so the information retained in the Z factor should be capture more global information. And then the Z vector is used as a conditional input to the invertible decoder. And since the decoder is invertible, so we can, with Z and gamma, we can exactly reconstruct our image X. And since Z captures more global information, and we expect that gamma can capture more local information. So that is, we can treat this reconstruction process as an addition operation. So I don't know if it's clear or not.
So I think a part of the question also was, is there a paper publication or an archive submission on this?
Actually, we are preparing the submission to archive. They are still, we still writing the draft.
Okay.
And I think we will release this submission maybe in the end of this week. Yeah.
Okay. There are more questions from audience. If not, then I guess we can conclude this. And thanks, Max, again. You will have a lunch break, and then you'll come back for more one-on-one meetings.
Thank you.
Okay. And thanks, everyone, for attending.
Thank you.